Morning to everyone present here. I am Sangeeta Lakshmi, working as Assistant Professor in UP Department, R.M.K College of Engineering and Technology. So today we are going to discuss about the subject RTL design with VHDL or Verilog hardware description language. So in the unit 1 is introduction to simulation and synthesis flow for the Verilog RTL. So these are the syllabus we are going to see in the unit 1, that is integrated circuit design methodologies, and then Verilog HDL, Verilog design description, and then finally we are going to see some important key terminologies used in the Verilog. Today we are going to see the Verilog HDL, that is hardware description language. Here the Verilog is standardized as IEEE 1364. Actually, the Verilog IEEE standard to describe our digital electronic circuits is IEEE 1364. It is universally. So the Verilog is more popular because it is the high level abstraction is possible here, and even it is popular for the verification also. Not only for the RTL design, it is also popular for verification. It was created by Prabhu Goyal, Bill Moorby, Chi Lai Huang, and Douglas Worm during 1983 to 1984 at Gateway Design Automations. So this language not only supports a synthesizable construct, it is also supports the non-synthesizable constructs, which can be used for design as well as the verification of digital design. So we have different types of Verilog IEEE standards. The first one, it is developed in 1995, which is called IEEE 1364 1995. Later, some modification has happened in the 2001. So that standard is IEEE 1364 2001, and then updation in 2005. So which is called IEEE 1364 2005. So we are going to see the Verilog design description. That means we can write the or we can describe the any kind of digital circuits by means of different coding writing style. So here we are using the three different coding styles, that is structural design, behavioral design, as well as synthesizable RTL design. So first we are going to see the structural design. In structural design, first of all, we have to know the overall structure of the design. Suppose, for example, if you want to design the 1-bit half adder, you have to know the exact structure of the half adder. You can see here, you can see here, for this 1-bit half adder, A and B is the input, and sum as well as carry, both are output, right? So we have the four different combination described in the truth table. The truth table will give you the relationship between the input as well as the output, right? So here the main intention is to describe the logic in the form of gate or block level. For example, it is the gate level. Okay, gate level is also called structural level. Block level means, suppose if you want to design the 8-bit ripple carry adder, right? 8-bit ripple carry adder, that time we have to write the structural method. In that we are calling the 8 times the full adder. Only one time you are writing the full adder program, but you are calling that full adder program for 8 times. So that is called as instantiation. So instantiation means creating the copy of that particular design, right? So 8-bit triple carry adder requires 8 times instantiation of full adder. 16-bit triple carry adder requires a 16 times the instantiation of full adder. So here the full adder is the block, right? So we are using the 0th full adder, first full adder up to we are using the 7th full adder. So these all called as block level. So this structural will support gate as well as a block level design using the net connections. Okay. It is mainly the instantiation of different small complex digital function. I told you, no, the full adder you are using, this is the small complex digital circuit which can be used to design your complex 8-bit triple carry adder, right? So it is basically the design connection of small modules to realize the moderate complex logic such as ripple carry adders, carry select adder, like that. Okay, so this is the example of half adder we are used in the structural code style. So always the program is start from the module and it is complete at the end module. So here you know the inputs are A and B and outputs are SC, that is sum and carry, and these is called as port list. So in this, out of these four ports, which are input ports, which are output ports, first we have to declare, and then it is structural model. Here we are using the two blocks. One is called as XOR underscore gate. Another one is called as AND gate. Right? It is XOR underscore gate. It is the AND underscore gate. So two block level you are using for your structural design. So it is a top level module. For here, we have to describe these two modules in the separately, which is the submodel programs. So here first I have written the submodel program for the XOR underscore gate, and the next one is AND underscore gate. So here XOR gate. XOR gate is used for what? Actually, you know the structure of your half adder, right? So in this half adder, if you want to produce a sum, you need the XOR gate. So the inputs is A, it is B, the output is sum. So here I have to write the assign. It is the continuous assignment statement which can be used for the combination circuit, because it is the actually the S is nothing but the net. Okay, the data type of here we are using the S is the net. That means whatever you are assigned at the right hand side, it is immediately assigned to the left hand side. That is called net. So the assign statement we are used for the combination circuits, right? So in the XOR gate, we have used the operator. This is used for the XOR operation. So assign S equal to A XOR B. Again, it is end with the end module, right? Similarly, here another module AND underscore gate. The input is wire. That is, here we have directly declare input wire A, or else you can write here A, B, C. The next step you can write input A comma B, output C. So like that we can write. But all the lines has to end with the semicolon. Okay. Finally, that is, this is the option is available in the Verilog. In a single line, we can write the program. This is the code efficiently we can write. So next, if you want to produce a carry, you know that it is the AND operation, right? So truth table, it clearly shows that if you are having input A, B, 0, 0, 0, 1, 1, 0, 1, 1, sum is you will be getting 0, here 1, it is also 1, it is also 1. So which kind of gate we have to use to get this output is, it is clearly shows that, and the two different inputs will produce the output means that is called as XOR gate. Okay, here for 1 the sum is actually it is 0. So two different inputs if we are using, the output is 0 means that is XOR gate. For carry, you know that it is 0, it is 0, it is also 0. If 1, 1, if you are adding, you will be getting 10. So 0 will be putting at the sum and carry here. So in this, you can compare with the input as well as the carry output. You just compare these two. Which adder is required to design your carriers? It clearly shows that the output only you are getting if both the inputs are 1, 1, right? So then only you are getting the output 1. Remaining all other combination you are getting 0. That means it is obviously AND gate. So AND operation, this is the AND operator. You have to use A and B. So this is the way we have to write the program in the structural code style. The next, we are going to see the RTL schematic of this design. So if we are running the uh, if you are running this program in the Xilinx 14.7 software, you will be getting the RTL schematic like this. This is the top level schematic. So in this schematic, it shows clearly that you have used these two blocks. One is XOR underscore gate, another one is AND underscore gate, right? It clearly shows. The next Verilog behavioral code style we are using. See, if you want to write the program in the behavioral style means no need to understand the that is exact structure of the that is in terms of gate level does not required here. Only thing is you have to know the exact behavior of your design. How we can understand this from the truth table, the relationship between the input as well as the output will give you the relationship. So by using that relationship, you are going to design your intended design. Here half order we have taken the example. Here that half order we are assuming that it is a black box. Inside the black box we don't know whatever it is. Okay. So without knowing inside the black box, only by understanding the relationship between the input and output, you are going to write the program, right? So here you can see the Verilog program. It is also start with the module. The name of the module here is it is basic underscore Verilog, or else you can give half underscore adder also. And then port list A, B, S, C. And then you have to declare what are all the input ports and output ports. Here it is a behavioral level. Always you have to declare the output as register. Register means the sum as well as the carry has to hold the data, right? So we have to declare the sum as well as the carry as a register. Then it will start with the always block, always at ARB. ARB here it is nothing but the sensitivity list. So if there is any change in the input A or B, immediately the next the statement inside the always block has to start to execute. So here if A conditional parameters given here, conditional operator we are using, if A is equivalent to B, if A is equivalent to B, the sum equal to 0, right? It is, we are getting only from the truth table. We know that for the sum, if both the inputs are same, definitely it is 0. Else, the sum is 1. Okay. It is only for sum generation we are used to this always block. The next always block is used for carry generation. Here we know that if both the inputs are 1, then only the carry will be 1. So we have to write the condition if A and B. If both are multiplying within the bracket, if it is 1. If true, A and B is true, C equal to 1. If it is false, C equal to 0. Okay. So this is the another way of writing the program, right, by using behavioral design. Here we have used the two always block. Even we can use a multiple number of always block. All the always block will execute at the same time. That is, at 0 simulation time, all the always block will start. But inside the always block, each and every statement will executed sequentially. Okay. So next we are going to see how this program will generate the RTL schematic. So this is the RTL schematic we are getting from the Xilinx 14.7 software. In this, we can see in this top level model which consists of AND gate, because the carry it requires the AND gate, because you have used the program like that. If A and B, C equal to 1. So you have used this. But the sum generation, you have used the A is equivalent to B, that is you are comparing. If A is equivalent to B, that time S equal to 0, right? So that condition you are making, that is comparison is making here. So it uses the comparator model. Just you can compare this arterial schematic with your arterial schematic which you are obtained from the structural design. So in the structural design, it shows the AND gate as well as XOR gate. But in the case of behavioral, you are having AND gate as well as a comparator. Okay. The next one is synthesizable RTL. It is also higher level description. It uses the synthesizable Verilog construct because the Verilog supports both synthesizable as well as the non-synthesizable Verilog construct. But here the RTL code is using the synthesizable Verilog constructs. Okay, it is many times if you are seeing this RTL coding, it may resemble as a structural or else behavioral model only. Okay, the main intention of the designer is to infer the intent and logic by using synthesizable Verilog construct. Actually, after writing the program, you want to create the gate level netlist. That is our main objective. So, by using this synthesizable RTL, you have to know for your logic what all the gates are required, right? So, the main intention of the designer is to get the information of your logic by using synthesizable Verilog construct. So, if any code which infers the gate level structure during synthesis, we can see it as the RTL disk. Okay, so here also you can see the RTL code. In this, the same way, the initially the module is started and end with end module, and in between that, port declarations are over. Similar to behavioral, here also the sum and carry we have to declare as registers, and then functionality design. Inside the functionality design, we have to use always block, right? Sensitivity list, ERB list. It is similar to your behavioral, but there we are using the comparator because we don't know what kind of structure we are going to use, right? So in the behavioral, by using a truth table, we know that if we are comparing the inputs, we can make the decision that sum is 0 or 1. Here in the RTL design, we know that a sum is required the XOR, that is operator we have used, and carry we have used the AND operator. Okay. So for this RTL coding, what is the top level schematic we have seen now? We are obtained this from the Xilinx software. So here it is clearly shows the AND gate as well as the XOR gate is required for your half adder. It resembles the structural design, right? So with this, I will wind up the session. Thank you all.